Yes, so with the inevitable culmination of my perilous dream, almost doomed to failure, also known as my PhD thesis, I figured it was time for a little bit of a retrospective on some things I've been thinking about and maybe some time for some, weakly justified philosophical pontification on all things programming. So, with that said, this all comes from the Codefns project, and the Codefns project, most of you know it as the APL compiler that produces fast code on the GPU. But we're not going to discuss that at all today. Instead, we're going to look at the ideas and the research contributions of the Codefns project and some of the more soft meta lessons that I want to push out there a little bit, maybe clobber you over the head with Thor's hammer of APL on it. And, the idea somebody suggested to me was I say, I'm not going to name any names today, and then just flash up an icon and the logo of every company here. But I decided, no, I'll tell you straight out. I think that a lot of the APL community thinks that some of the ideas in here are pretty obvious, but I don't think they're put into practice nearly as well as we think. And I think there's a lot of influence from the outside, which is valuable, but there's also a lot of mythology in modern computer science that really needs to be challenged, and we need to push a little bit on it. And I feel like I can talk a little bit about this now because of the Codefns project. So, as a research project, why do we care? Well, because it shouldn't exist. Because when I started this, and probably for the next 3 years afterwards, most people, A, didn't even understand what I was saying, and B, once they did understand, said that's fundamentally impossible, except in theory as an intractable problem somewhere inside of the space of computability. But outside of that, translating that into real world, they basically said, no, never going to work, not going to happen. Well, what we have done instead is we now have a compiler, and the compiler itself, the tree transformations that have to happen from taking source code and converting that into something that can run on the computer. That set of tree transformations, the research contributions, we've done that in APL. I've implemented these transformations, and we've benchmarked them. And the question is, how fast and how much memory does this compiler use while it's running? Well, every good performance talk at a computer science conference has a graph going up and to the right. Unfortunately, when you run this on Dialog, there's not really much up and to the right here. So this is the speed-up graph of the compiler running against the way you would traditionally write this compiler. So we've got a compiler that's written in APL and a traditional compiler that's doing the exact same stuff written in the state-of-the-art traditional compiler frameworks. And this is the traditional version is a DSL that's specifically written to help compiler writers write compilers. So these numbers here, those are base 2 log scale. So everything here is 2 to this number, right? So this is your data size here. So we start with basically 1,000 nodes at our 0 state, and then we go up to 1,000 times 2 to the 14 for our number of nodes in our tree. And here we have the speed up. And you'll notice that Dialog, this is an interpreted language running on CPUs compared against the traditional systems, is achieving 33x performance improvement over the competition. But this doesn't work for the computer science people because this is not a graph going up and to the right. So, if we run it on the GPU, we get our nice graph going up and to the right. Again, base 2 log scale, same system. But notice this. We get 200 times performance improvement over the traditional version. And these are very, 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 very small numbers. This size is 1,000 nodes in the tree. You can write Black-Scholes and probably get 1,000 nodes in your tree, right? This is not that much larger. This is not a lot of source code. But we never really get worse than about half the speed of your traditional compiler, even when we essentially have no data on the GPU. That in and of itself is kind of an interesting thing. So, then the next question for every good computer scientist who's wondering how fast does something run? Well, you've got the execution speed, and then you have memory usage. So how much memory does this thing use? Well, when you load it into Dialog, on the large size, the 2 to the 14, we're looking at a pretty hefty 63 megabytes to run, to load in this AST. So, it's a little bit of data. Not much by anybody's real scale if you're an APLer, but, it's not trivial. So what does the traditional system run? Anyone want to take a guess?
Same thing, but with a G.
Yes, the equivalent AST in the other systems is from 1 gigabyte to 1.4 gigabytes, depending on the system that I tested. Yes? So who's the competition? The traditional systems are scheme implementations. One's Racket and one's Shea Scheme, both written on the NanoPass compiler framework. And it's about 1,000 lines of code for the traditional compiler. So the lessons here is that, the fact that you can do this at all is really, really interesting. But for us, this also leads to some really interesting questions about the software design aspects that led us to getting here. Why could this be done here when people said it was impossible in other things? So to give you a little bit of a context for this, let's get down to business a little bit and talk about design. So some of you will remember that I have a t-shirt with a version of my compiler on it. It's a bit of code on the front, bit of code on the back, Codeiphones on it. It's not bad. But that's not what the thesis is based on. That was an early prototype. So what are we talking about now? And another rule in computer science talks is don't show any math. Avoid showing too much code. Don't talk about the math. Get the big ideas across. Nobody cares about your code. Well, I'm going to violate that today rather harshly. But the good news is that I'm not hiding anything here. This is the compiler. This is the whole thing, including comments. So, the question now becomes, well, is this a useful compiler? Now, I'm not going to force you guys to go through this today. However, a quick scan will hopefully reveal that there's really nothing special here. This is standard APL. There's nothing tricky here, nothing going on. But this is domain, research hard problems because we didn't know how to do this before, and it did take me a while. So my GitHub repository has been storing this information, and somebody pointed out to me, I've been working a lot on those lines of code. So this is the GitHub additions and deletions on the Codeiphones repository. To get to that. So, but now that I've got to that, the thesis, as it's written, and it's available, so if you guys want it, I can get you a copy, is basically a textbook that goes line by line, piece by piece, character by character, and explains how you can do that too for any of your tree transformation problems. So any of the problems that you're having in terms of manipulating tree data, you now have a textbook that will show you how to do this. And you can ignore most of the other sections because that's the sections necessary to explain it to non-APLers. The APLers can pretty much jump right into the middle and they'll be doing well. But that leads to another interesting question of how come I don't have any comments? That's a big thing. People say, oh, well, you don't comment your code very well at all. They're like, Well, I did. I wrote a thesis on it. And so as it turns out, the number of words that it takes to explain those 17 lines of code in a sufficient manner to an academic committee who's supposed to be experts in computer science is about 66,000. So, if we translate that into actual lines of text, we're at about 6,920 lines of text. So, if we actually look at the level of commenting in my code, I don't disagree with comments. I have a comment to code ratio of over 400. I think that's pretty good. So all of this is kind of stark, and it's kind of off the wall. And so some questions is, what are some lessons that we might be able to pick up from doing this kind of stuff? And so I've come up with what I would think of as 10 sort of philosophically oriented lessons that maybe we should think about. And if everyone fundamentally agrees with all of these all at once, and you're all, yeah, you're absolutely right, I think we're not thinking hard enough. So it's okay to be a little combative here at this point. If you do want to jump up and mug me, try to take this path and don't climb over the tables. But I think we'll start off slow here. So the first one is good enough is the enemy of the future. So how many people have heard of good enough is the enemy of best? But you've also got the equivalent in software, right? Everybody says good enough wins, right? The two schools of thought, Unix school of thought versus the MIT school of thought. There's a paper on that you can look up. If you try to do too much and do too perfect, you're going to fail. Instead, you have to go for simplicity, do this piece, and don't try to make it feature complete. Just do the basic stuff. Just get it good enough. Well, there's an aspect of that that's absolutely 100% true. But what we've had is we're now almost taking that so far in such the opposite direction that now we've got software that's reaching a cascading failure because it's built layer upon layer of good enough. And the problem is that once that happens, you've got complexity that is hidden there, that's destroying your software and causing essentially heart attacks inside of your code bases. This is not very good. And so you need to think about this, because I think philosophically, people have this attitude. And you have to fight the perfectionist attitude, but you also have to fight the attitude of not thinking about making continued fundamental excellence improvements in your software. You need to think about the concept of excellence when applied to your software, not necessarily perfection. So one of the aspects of this is the next rule, which is simplicity is not optional, and nor is complexity required. And again, I'm going to say this is in direct contrast to the current status quo in computer science. Everybody just assumes complexity is a given. You can't handle it, you can't deal with it, there's no way, so the only thing we can do is try to survive and stay afloat and do everything we can to manage that complexity at some level. And so then we build bigger and bigger systems to create more and more safety measures to help support an infrastructure, all this stuff, and it's killing us. And so what we end up with is huge software pieces that are impossible to analyze, impossible to think about, impossible to reason about. And the result is software that has bugs in it that we can't trace and fix. Software that once we find the bugs in it, we can't actually fix those bugs because the re-architect is so difficult that it doesn't work. Or we have any number of other things. A classic example is Visual Studio. I think somebody sent me an error log of the Visual Studio bug report on something that they had their IntelliSense taking like 50% CPU on this and using gigabytes of memory. And they eventually traced it to some little quirk in the way that their architecture was designed, because everything was shoehorned together over time, and nobody had worked on addressing the fundamental questions of that code base from a big picture perspective, which they really needed to do. And part of this is speed is not a luxury. Everybody thinks of Knuth's premature optimization as the root of all kinds of evil. Well, okay, kind of true. But thinking about speed is not premature optimization, because the right point at which to do architectural optimization is before you've written all of the code that you can't change again. So another aspect of this is a compiler guy once said, I don't really work on making my compiler too fast. I just try to avoid doing stupid stuff. And his compiler was the fastest compiler in the field. So the key is not to, we're not trying to do some ricing over the top drag racing. We're trying to make sure that our systems take speed into account and take efficiency into account from the beginning at the right level. And part of this is managing your memory. So that 1.4 gigabytes, where did it come from? Why was it there? There's nothing fundamentally different between the two pieces of data. They're representing the exact same AST with the exact same amount of nodes. Why is one representing it as 1.4 and the other as 63 megabytes? Well, you need to control that memory usage, because modern CPUs, a lot of your problems, tree transformation, data manipulation, a lot of that, it's down to your memory usage. It's down to your memory management. It's how efficiently you're accessing those memory patterns. And so you need to be aware of how that stuff behaves. Otherwise, you'll make architectural design decisions thinking that you'll deal with the speed problem later, and those architectural decisions will have encoded a fundamentally inefficient approach. And that's going to cause a lot of problems. So that's a little pie in the sky. What about something more concrete? Well, this is pretty concrete. Almost, dare I say, concrete ice cream. We got a serious problem. And the reason that the 1.4 gigabytes you saw there is because of pointers, references. Anything relying on that nice, chunky, juicy 64-bit reference to somewhere else. Because it's one of the least efficient methods that we have for representing a lot of our data right now. And not only is it inefficient in terms of sheer memory usage, the garbage collected approach that we use and the fast allocation and the chunking in small pieces and the graphs and the way we allocate them, all of this stuff results in systems that have massive memory fragmentation, that are extremely difficult to parallelize, and are extremely difficult to manage their memory. If you go out to a standard programming conference and ask people, what's the memory layout of this machine? What's the access pattern going to be? How much memory is this thing going to consume? They'll be like, we might be able to figure that out through testing, but that's probably not very reliable. That's a very bad state to be in, because now that compiler framework was built on a system built on pointers, and those data abstractions are built on pointers. Nobody can fix that except the language implementers, because everything else above that is built around that language. So you've just created a giant stack where you cannot fix your performance problems now. It's not a premature optimization anymore. It's a fact of you've picked a model that's not going to work on your machines to scale anymore, and that's a big issue. So, one of the general things that we should do now is stop thinking of parallelism as an afterthought and stop thinking of parallelism as a difficult task. If you do your language design right, APL tries to do that, you default to parallel thinking, default to parallelism, and only start to serialize things at great need. And I mean great need. There's almost never a reason to really drop this parallelism. That doesn't mean you're always going to use it in the runtime, but it does mean that you don't need to sit around and introduce arbitrary specifications on ordering of operations in the way you write your code that makes it difficult to get parallelism out, because all machines are parallel programming now. We don't have machines that map to the model of C anymore. To get performance on your modern machines, it is data parallel fine-grained programming, coupled with then task parallelism on top of that. There's not anything else that's in modern use anymore. Maybe the low micro ARM machines, but even those are getting vector lanes in them. So start your thinking with parallel programming. Build your models of how to solve problems around parallel thinking. And in fact, it's more natural, but that's for another talk. So a part of this aspect is, instead of doing this, using the machine to tell us what to do, give us instructions and guides, instruct, value the human resource, because that's the one who's really going to solve the problem. That's the brain, the machine that can see the patterns and the big picture and the value judgment and the business questions and the things that are necessary in order to solve the real problems that are going to come and bite you 2 or 3 years down the road and kill your project, or make a foundational problematic, introduce a problem that's almost impossible or very, very, very expensive to fix. So you want to value those human resources and value programming from a human perspective rather than trying to leverage the machine to get rid of the human faculty. Leverage that human faculty as much as possible and design your systems to leverage those human faculties rather than making the machine the master. And if you look at a lot of programming today, it's about making the machine the master and about making the human a robot. And I think that's the wrong approach. And a part of this is you need to embrace ascetical programming. Feel the burn. Okay? Now why? What am I saying here? I'm not saying suffering for suffering's sake. I'm saying suffering to reach a good end. Suffering for the cultivation of our source code and ourselves so that we become better programmers and solve our problems in better ways. Because if we make it too easy to hide complexity, if we make it too easy to avoid pain in our source code, and so then we start writing all these things that allow us to easily hide complexity. Anytime that you start making it easier to add complexity to the system, then it's easier to simplify and solve the solution in the right way, you're really running a dangerous game. Now, of course, the real world means you're going to have to adapt and adjust as things fly. This is not some rule that sits in the stand and is concrete, but it's a principle about trying to design your systems so that to work with the human mind so that you're incentivized in every direction that you work and look to write better code rather than writing worse code. And to that end, competency trumps safety. That doesn't mean that safety is unimportant. It means that when you start designing your systems around creating walled gardens so nothing bad can ever happen, at the cost of maximizing the human competency involved in your code, well, suddenly you've solved all the obvious problems that you could see, but those aren't the problems that you need to worry about. You need to worry about the problems you can't see. And the way to push those at bay is to expand the competency of your programming so that you can see what's coming, you can see those problems, you can see a wider space and work around it, rather than trying to hide in the sand and make sure that nothing bad ever happens to you. Now, that means you have to leverage safety. You do have to take careful consideration of how to leverage safety in a useful manner. But safety in and of itself is kind of an idol that people have just sort of started chasing down the road, thinking that it's the panacea that's going to solve everything. Static typing, functional programming, I'm looking at you. But it's not really that. They're missing the point. And they're willing to cause degradations in competency within their programming base, or make it more difficult to be equally competent with the problem set you're working with, just so that you can be more safe. And I don't think that's a good trade-off. And the other aspect is one other piece of coding priority that I think is relevant. And that's beauty and truth. We've got this practical mindset on some level, and that's good. But sometimes the beautiful things are the very things that help us to see something meaningful and important inside of that code that we need to see. And the beautiful code is often the code that allows us to perceive a bigger picture better and more easily and solve the bigger problems. So rather than thinking of beauty as an optional aspect of your code, think of it as a technique that you can use to start improving the source code and seeing and solving more problems. Now, philosophy lesson over. Let's debate. Thank you.